So let's read the problem first. Convert the following integral in cylindrical coordinates to an integral in spherical coordinates. So we're given an integral in cylindrical coordinates. We're going to spherical. So we're switching coordinate systems. So the integral is 0 to 2 pi, integral 1 to root 2, integral root 2 minus r squared to r, z squared dz dr d theta. And for reference, they even marked, if you think about it in terms of r and z, this is the region that you're going over in what we would call the RZ plane. So this is to help you visualize and figure things out. So we have 5 possibilities. I won't read them all. Do we have a guess? Maybe not more than just a guess.
C.
C? It's not C. All right. We're up in the back.
A.
Ooh. Not A. B. Not B. E is correct. You beat last year. You got it in 4. Okay. Now you might be a little bit suspicious about this answer. So let's go through it. All right. So let's think about what's going on. We've got to convert, so we have to worry about 2 things. Bounds and what we're actually integrating. Which one do you want to tackle first? We'll have to do them both. Bounds. Okay, so the good news is they gave us our picture. The other good news is because we're going from cylindrical to spherical, whatever happens to the theta stays the same. So the outer layer still stays 0 to 2 pi. That doesn't narrow anything down. All right. So, but, we might as well make a note. Theta goes between 0 and 2 pi. Now let's talk about our phi. So we can still use the same picture here to figure out what's going on in terms of spherical coordinates, because we have that rotational symmetry. So we look at a slice. That'll help us figure out. In spherical coordinates, everything stems from the origin, your center point. So we say, okay, phi equals 0 is up here. We're not hitting our region, we're not hitting our region, we're not hitting our region, and then boom, we're hitting our region. So what angle are we at when we start hitting our region? Pi over 4. We come off pi over 4 because phi is off the z-axis. And then we're like, in our region, 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 stop. What's the angle? Pi halves. So, phi goes between pi over 4 to pi over 2. Okay, now, that does knock some things out. For example, this one, 0 to pi over 4 is out. That also knocks out d. That's why, of course, nobody guessed d. It's obviously not right. Okay. Well, what about rho? So rho, you say come out from the origin. You think about where do we start hitting our region, where do we stop hitting our region? We start on this piece of the circle, but this is really, a slice. So what is that circle really representing? Sphere. If you turn the circle, spin it around, you get a sphere. So we're hitting the sphere at root 2. Well, it turns out spherical coordinate loves spheres. It's in the name. So we start at root 2. Start at the sphere. Where do we stop? Well, we stop at that line. In the RZ plane, what is that line? Yeah, r equals square root of 2. Now, the problem is, that's not rho. But can we rewrite r in terms of rho? Yes. It's almost like there's a formula for it. What's the formula? Rho sine phi is r. Now, I want to get rho by itself. So what do? Move the sign across. So you divide by sign. 1 over sine has another name, cosecant. So root 2 cosecant phi. So where are we at? If we go just by the bounds, we are now narrowed down to 2 possibilities, C or E. So one of those is correct. So we've knocked out 3 possibilities. So that's good. All right. So far, so good? Now let's get to what we're integrating. Does something seem missing here? Is something not there which should be there? R. Why should that be there? Because when we talk about pieces of volume, we have an R dz dr d theta. So what we should really think of this as is z squared over R times R dz dr d theta. That's might be why C looks so tempting. This is our dv. In spherical coordinates, what is our dv? Rho sine of phi d rho d phi d theta. Or you look it up. That also works. All right. So that's the part on the end. You have to add the R to get that in. Now we say, okay, but we know R is rho sine phi. So we're going to divide by a rho sine phi. And do we know how to write z in spherical coordinates? Z is rho cosine phi. And that is being squared. Well, you can cancel a sine. You can cancel a rho. You have rho squared times another rho makes rho rho cubed. Cosine squared phi d rho d phi d theta. So the answer was E. All right. Good. Whew. What a fun problem. Any questions on this one? Nice warm-up problem. All right. Well, good. Well, you'd be ready for it if it was on the exam. It probably won't be. But if it were, just imagine. It'd be great. Okay. Well, we'll have our thought for the day. And this comes from Richard Feynman, very famous physicist. Very colorful character. If you watch the movie Oppenheimer, the Oppenheimer was full of real-life personalities being portrayed. Richard Feynman was one of the people that was portrayed. And so what did he say? He said a lot of cool stuff. But the one for today, I learned very, very early the difference between knowing the name of something and knowing something. And I think this is oftentimes what sort of separates people who are comfortable in a discipline and people who are not comfortable. Because you might say, oh, yeah, sure, I know about it. I've heard about it. But just because you know what something is doesn't mean that you know how to use it. Like even the formula sheet. It's like, oh, sure, I know the formulas are there, but do you know how to use them? Everybody has that same level playing field, but not everybody knows it at the same depth. And I encourage you to know things which are important. All right, now what's our goal for today? Last time we sort of motivated our change of variables and wrote down the important formulas. Today is practice. We're going to practice change of variables. Change of variables has different names. Sometimes it's called multivariable substitution. But whatever you want to call it, but that's what we're practicing. So we start with something involving x and y. We want to switch to something involving u and v. Why do we do this? Well, in the hopes that by changing, making a substitution, we'll make something that's easier to do. Because our goal is to be kind to ourselves. We want to have success, and if we can make something simpler, we can achieve that. And there's the basic plan: handle how you break things up, rewrite the function, rewrite the boundary curves. And instead of talking about that here, I'm just going to grab the slide from the end of our last class where we went through this. So, we went through this, we sped through this at the end of last time. Step 1, identify the substitution. It's usually super simple. 95% of the time, the way you identify it is they tell it to you. And the other 5%, it should be hopefully somewhat clear. You would say, would we ever encounter that 5% in real life? Real life, that's hard to say. On a quiz? Yes. Unfortunately, they put one of them on the turn-in. But don't worry, it's not as bad as it looks. So how do you find it if it's not given to you? Well, you think about what's going on. You're trying to simplify your integral, and you say, well, there's two places that things could get complicated. There could be strange functions, or there could be strange boundary curves. And those are the two things you look at and say, can I do something to make one of those two things simpler? And that's where these substitutions are coming from. They're being driven by what's happening with the function or what's happening with the boundary curves. All right, now once you've identified the substitution, there's 3 parts to your integral, and that's these steps 2, 3, 4. Now, in principle, you can go in any order, but in practice, always start with what's called the Jacobian. That's the how do you break things into small parts piece. And so if you have u and v as functions of x and y, you get that the Jacobian, ux, vx, uy, vy, dx, dy is du, dv. This part is on the formula sheet. And this is what we want you to learn how to use. So you don't have to memorize this, but you do have to know how to use it. So that's what we're going to be practicing. And why do we want to do the Jacobian first? Well, if you think back to our warm-up, we had to sort of do a correction by adding this extra piece that's involved with the little piece of volume. Essentially, that's going to happen in some cases where it says, this might be something non-trivial. You're going to say, okay, I'm just going to borrow from my function and set that aside. And then my function somehow is a little bit smaller. So that's why I want to do it before I rewrite the remaining part of the function. Remaining because I may have grabbed something for the Jacobian. This will make it become more clear as we do some examples. All right, so rewrite the function in terms of u and v. Now we have to rewrite the region in terms of u and v. And for this is my advice. Sketch your current region in terms of x and y. And say, what are the curves which bound your region? Identify each one as a function of x and y. Once you have each of those curves, rewrite the equation for those curves in terms of u and v. And those are your new curves that bound your new region. And then if you draw it, your region will pop out. But once you have those 3 parts, those are your 3 parts of every integral, you combine and you're done. With at least the rewriting. Okay, so that's the plan. Now, the practice. Okay, so our first round. Find the integral from 0 to 1, integral x squared plus x to x squared plus 1. And we went ahead and drew this picture. So this is what the region looks like. Of the function 6x over 1 plus y minus x squared cubed dy dx by carrying out the change of variables, u equals y minus x squared and v equals x. So we can see it's a change of variables. And they're going to make it pretty clear. And lo and behold, we don't have to think very hard to find what our variables are. So that saves us a step. So now we can get into working through the various parts. All right, so where to begin? Well, start with the Jacobian. So our Jacobian says du dv is equal to the absolute value of the determinant u sub x, u sub y, v sub x, v sub y, dx, dy, dy, dx. It doesn't really matter for right now. Mostly we're just saying, how do these compare? So we need to take these partial derivatives. What is u sub x? It's minus 2x. U sub y, 1. V sub x, 1. V sub y, 0. If you take this determinant, what do you get? Yeah. Well, you get negative 1, but then there's the absolute value. And so we end up with dx dy. So it turns out that for this case, du dv is dx dy. In the sense that there's no necessarily scaling, well, when I say scaling, there's no expansion or contraction. It doesn't mean that there's a one-to-one. Okay, so that's that piece. Woohoo! That'll make it easy. Next up, let's do the function. Okay, so for our function, we write it down. We have 6x over 1 plus y minus x squared cubed. That's the function. And we look at this and say, all right, we need to rewrite this in terms of u and v. We know what u is. We know what v is. And so we say, okay, how can we use the fact that u equals y minus x squared and the fact that v equals x to rewrite this whole expression so it only involves u and v, no x's or y's? How about the top? Is there a way to write that in terms of u and v? Yeah, 6v. How about the bottom? Yeah, 1 plus u cubed. And then we're done with that part. Nice! Woohoo! These problems are faster than we thought. It's almost like they want us to succeed. Okay. Now the last part, the boundary. This is the fun part. You grab the old shape, right? We take the current region, describe it, graph it. How many boundary curves are there to this region? 3. What are they? And what's this one here on the left? X equals 0. How about this one, say we'll call it below? It's the x squared plus x. And the one on the top, what is that one? Y equals x squared plus 1. So these are your bounding curves in the xy plane. But they're in terms of x and y. We need to move to bounding curves in the uv plane. So what we're going to do is we're going to take every one of these equations. So every boundary is an equation. Every equation gets rewritten in terms of u and v. Well, let's see if we can figure these out. How can we rewrite x equals 0 using u and v? Okay, v equals 0. All right, that one wasn't so bad. Nice, nice, nice. Y equals x squared plus x. Now remember, it's an equation. We're allowed to move things around. What can we do? So we can move the x squared across to make it y minus x squared equals x. And what does that become? It becomes u equals v. All right. Similar, We'll move the x squared across. Y minus x squared equals 1. What does this become? U equals 1. So what we did is we said we have our old boundary curves. So these are our old curves. And now we're switching to our new curves. Okay, so we need to do a quick sketch in the UV plane. Well, V equals 0. That's pretty straightforward. That's just a straight line. V equals 0. Shoop. U equals V. What does that look like? Yeah. It looks like similar to y equals x. So we have u equals v. And what about u equals 1? It's going to be a vertical line. U equals 1. And you'll see that there's one region that will pop out. There's one shape where these three lines are the boundary of that shape. So our new region is a triangle. But whereas our old region had this sort of curved sides going on, our new region is a much simpler triangle to describe. Okay, so we have all of our pieces in place. How do we break things up? Our function and our boundaries. So we put it all together. So we're going to do integral. We'll start with our function. So our function becomes 6v over 1 plus u cubed. Our dx dy is going to be du dv, or dv du. Let's ask a question. Since we actually have to find this, not just rewrite it, but find it, do we want to integrate first with respect to v or first with respect to u? V. Why do we want to first integrate with respect to v? Because it's possible. Yes, it is possible to integrate first with respect to u, but it would take us an hour. And we like ourselves. We think that we deserve good things. So we're going to do the one that's easier to do. So we say, hey, v is easier to integrate first, so let's integrate that first. We get to choose. Might as well make good choices. Now that we've made a choice, let's figure out our bounds. Where does u go from? 0 to 1. Given a u, where does v go from? 0 to u, right? Because these are v equals bounds. So v equals u. All right, well, we don't want to spend too much time because we have a few more to do. So 1 plus u cubed on down the denominator, that's a constant. That's just along for the ride for the moment. What's the integral of 6v with respect to v? 3v squared. Evaluate from v equals 0 to v equals u. That becomes the integral of 3u squared over 1 plus u cubed. Can we do this integral? 1 over 1 plus u cubed, partial fractions, not good. But this one, can we do this? The derivative of u cubed is 3u squared. So it's almost like if you do a substitution, and this is one that we hope you can do in your head. Set the denominator equal to something, I'll call it w since we're already using u. Then the numerator is the derivative. So what is this integral? Or what is this antiderivative? Maybe I should phrase it that way. Log of 1 plus u cubed. 1 over w dw. Integral of 1 over w is log w. Evaluate 0 to 1. When you plug in 1, what comes out? Natural log of 2. When you plug in 0, what comes out? Well, natural log of 1. But what is natural log of 1? 0. So there's the answer. And that looked like a miserable integral, but after substitution, not bad. Not bad at all. All right. Ready for the next one? Good. Here it comes. Using the substitution, u equals x squared plus y, and v equals x squared minus y, rewrite the following. Now it's not just one integral, it's two. One of them goes 0 to 1 minus x squared to x squared of 4x e to the x squared minus y, 1 plus x squared plus y squared dy dx. The other one goes 1 to root 2, x squared minus 2 to 2 minus x squared of 4x times e to the x squared minus y over 1 plus x squared plus y squared dy dx. Now, we can do this integral. In fact, if we're doing well on time, we'll probably actually do the integral as well. Notice that really what's happening is that these insides match. So the problem was our boundaries were really messy, so we had to separate into two integrals. So we really are going to think of this as one integral, just we had to write it as two to write the problem and get that going. So where do we begin? Well, it is a change of variables, and they told us the change of variables to make. So we're just going to move forward with that. Start with the Jacobian. And so we say, all right, what does the Jacobian tell us? It tells us that du dv is equal to the absolute value of the determinant u sub x, u sub y, v sub x, v sub y. And this Jacobian, it's very forgiving. So if you sort of mix it up a little bit, it'll still give you what you need. dx, dy. All right, so straight from the formula sheet, don't have to think about this. Now, we start saying, okay, so what are these pieces? What is u sub x? So you come up here, what is u sub x? 2x, u sub y, 1, v sub x, 2x, v sub y, minus 1. We take this determinant, and we're going to get minus 2x minus 2x. Take the absolute value of this, x is always positive, and we get 4x dx dy. Okay, so now it's a little more interesting. Yes, 4x. Now, don't panic. Here's what we're going to do. Let's look at what we're currently integrating. We're currently integrating, we have our 4x e to the x squared minus y over 1 plus x squared plus y quantity squared dy dx. We say, well, hey, when we switch to du dv, we need to get a 4x attached to dx dy. Is there such a 4x available for us to attach? Yes. It's right there. So we say, hey, move it over. So we're going to think of this as e to the x squared minus y over 1 plus x squared plus y quantity squared times the 4x dy dx. This part on the end, this is what's going to become our du dv. So that means when we think about rewriting the function, we're not going to have the 4x as part of the piece we rewrite. That's been pulled off. So when we go to step 2, that's why we want to do the Jacobian first, we asked ourselves the question, the part that remains, e to the x squared minus y over 1 plus x squared plus y quantity squared. Can we rewrite that in terms of u and v? I heard a yes. Okay, how do we do it? What does the upstairs look like? E to the v. Downstairs? 1 plus u squared. Okay. Now we've got essentially these two pieces. What's left? The bounds, the bounds. Don't forget the bounds. So, the first set of bounds, we're going from 0 up to 1, negative x squared, 0 to 1 up for y, I should say, negative x squared up to positive x squared for y. So if you sketch that, we have negative x squared, positive x squared, and we stop at 1. So this is what we're doing in our first piece. So I'm going to mark these curves. Then we say, aha, in the next piece, we're going 1 up to root 2 for x, and x squared minus 2 less than or equal to y, less than or equal to 2 minus x squared. Now, I don't have to draw much. I just think about what happens at 1 and root 2. So when I plug in 1 into x squared minus 2, where am I at? What is 1 minus 2? Negative 1. I'm right there. Right where this ended, I pick up. When I hit root 2, where is x squared minus 2? 0. So it's going to go up to root 2 up to 0. So it's actually starting down here. X squared minus 2 is a parabola that was shifted down. 2 minus x squared does the same thing, just flipped across. So you're going to start up here and go down. So here's y equals 2 minus x squared. Here's y equals x squared minus 2. And we go between. So that's our current shape. Cool. Cool, cool, cool. But we don't want this in the xy. What do we want? uv. So what do? List the bounding curves. How many bounding curves do we have? 4 bounding curves. So they are y equals x squared, y equals negative x squared, y equals 2 minus x squared, y equals x squared minus 2. These are our bounding curves. For each curve, we want to rewrite this now in terms of u and v. So keep in mind that u and v look like x squared plus y or x squared minus y. What can we do to our first curve? Y equals x squared. What does that become? Well, intermediate step, x squared minus y equals 0, or v equals 0. This next one, y equals negative x squared. Intermediate step, x squared plus y equals 0, which becomes u equals 0. Next one, y equals 2 minus x squared. That becomes x squared plus y equals 2, or u equals 2. Last one, intermediate step, that's x squared minus y equals 2, just moving the y and the 2, having them swap places, which becomes v equals 2. So, while our region in the xy plane is kind of messy, we have these 4 parabolas. In the uv plane, what do we look like? We're a square. It's hip to be square. That's our region. A simpler region. All right, so we put it all together. And what do we get? Well, we're going to have an integral e to the v over 1 plus u squared. Is there any advantage to du dv or dv du? No. So we'll just pick one. Du dv. What are the bounds for v? Where does it go from? 0 to 2. Bounds for u? 0 to 2. So technically, this is the answer. And we're done. But just for funsies, could we integrate this really quick? Because I have a suspicion. Well, because this is a nice integral, that's a technical term, constants in the bounds, and here you can separate the v parts and the u parts by multiplication. You can do the two integrals separately. So I can do integral 0 to 2 e to the v dv times it by integral 0 to 2, 1 over 1 plus u squared du. Integral of e to the v is e to the v. Evaluate from 0 to 2. When you plug in 2, you get e squared. When you plug in 0, you get 1. Yeah, be careful. A lot of people forget to do that when you have an e around. Integral of 1 over 1 plus u squared. You knew there was a reason I had to do this integral. It's arctangent! Yes! What? Who could have thought? Oh my gosh. Evaluate from 0 to 2. Now arctangent of 0 is 0. Arctangent of 2 is arctangent of 2. And so there's the numerical answer. So this looks like a really hopeless integral, and that's because as written, it's hopeless. But changing by substitution, we get hope. All right. So let's do at least, we have time. Once more to the breach, dear friends. Once more. This comes from an old exam. And someone said, one of the other instructors said, we always have problems and they don't do anything interesting. And I said, hold, I was going to say hold my coffee, but I don't drink coffee. You know, hold my bottled water. The students are going to love this. So this is the problem. And before we start, if we have enough time, we will actually be able to not only rewrite it, but we can actually find the integral for this. We can find the exact value for this integral. Now, the reason I mentioned we can find the exact value for this integral is I plugged this into Wolfram Alpha yesterday, and Wolfram Alpha said, here's an approximation. I'm not going to give you an exact value. So it couldn't do it. So we can still beat the machines, right? We have not been replaced by machines yet. I haven't. No, you haven't. Okay, all right. So we have our change of variables. So we're going to go through. This will seem very familiar now that we've done these things. They handed it to us, so we're not going to question their gift. We're going to use it. So we say, all right, we have du dv, absolute value, u sub x, u sub y, vx, vy, dx, dy. So u sub x, 1, u sub y, v sub x, v sub y. When you take this determinant, what do we get? 2y. Do we have a 2i handy? Yes. So this 2i in the front is not part of the function in terms of the substitution. It's going to attach onto that dx dy. That's going to become our new du dv. So we say, cool. Now we have to handle the other piece here, this cosine, x plus y cubed minus 3 times x plus y. So we look at this and say, can we rewrite this portion using u and v? Yes, we can. What is it? U cubed minus 3u. Okay, cool. Now we're 2/3 through it, right? We found the Jacobian, we rewrote the function. What's left? The bounds. Well, good news, they drew us a picture So I'm going to go ahead and just mark some things here. This is in the xy plane. So this line, do you recognize what that line is? Y equals 1. This line, x equals 0. This line, y equals x. Okay. Oh, wait, that's not y equals x. Y equals x is this line. This is x equals 2 minus y. Sorry. All right, so we have 3 lines. Each line is going to become a curve in the xy plane. Sorry, in the UV plane. And 2 of them are fairly straightforward, and one of them is a little subtle. Which ones do you want to do first? Okay, so you went with the non-subtle one. Excellent choice. For x equals 0, not really obvious thing, right? But let's use this. If x equals 0, plug in x equals 0. You get u equals y, v equals y squared. What's another way to write that using just u's and v's? Yeah, if you substitute in, this tells us v equals u squared. Okay, x equals 2 minus y. What's another way to write that one? X plus y equals 2, or u equals 2. Y equals 1. V equals 1. So now we have our 3 curves. Okay, so in terms of the UV plane, we have v equals u squared, that's the parabola. We have v equals 1. And we have u equals 2, which means I drew my picture not very conveniently. That's okay. You can always redraw. So here's v equals 1. Here's u equals 2. And here is v equals u squared. So what we get is, instead of this triangle, we get this triangle. Nice. Nice. Okay. Now let's put it all together. Here we go. So we're going to get integral. This part is cosine u cubed minus 3u. The other part, this 2i dx dy, becomes du dv or dv du. Which do we want to integrate with respect to first? We'd rather integrate with respect to v. Now, we look at our picture and say, well, we need some things. This point right here happens to be at u equals 1. Because if you put in v equals 1, you get 1 equals u squared. And now we say, okay, where does u go from? 1 to 2. Now, given a u, what does v go from? 1 to u squared. Okay, so you integrate this. This is the answer, but I want to finish the problem because we have a few minutes left. We do have one more thing to talk about, but we can finish this. Finish it. Finish it. This cosine of u cubed minus 3u just comes along for the ride. Then we have v evaluated from v equals 1 to v equals u squared. Very suspicious here. That's an interesting thing that we've been asked to do. When we carry this out, we get the integral 1 to 2 cosine u cubed minus 3u times u squared minus 1. Just plug in v equals u squared, subtract v equals 1. Now, is this hopeful? If you substitute t equals u cubed minus 3u, what does dt become? 3u squared minus 3. Or 1/3 dt is u squared minus 1 du. So this becomes the integral. You plug in 1, you get 1 minus 3 is negative 2. Plug in 2. 8 minus 6 is positive 2 of 1/3 cosine t dt. Well, it turns out cosine t is integrable. So this becomes 1/3 sine of t from negative 2 to 2. And if you plug that in, you can take advantage of the fact that sine is odd. So this becomes 2/3 sine of 2. So we can answer this. Wolfram alpha can't. Yes. Score 1 for us. Now, I have 1 minute left. And I want to mention something. Because I promised you, there's something I promised we'd talk about which we haven't talked about yet. It's where does the rho sine of phi come from? So here's the thing. You don't have to memorize this. I just want to explain it. We talked about Jacobian for 2D. You can do Jacobian for 3D. The way it works is that if I want to think about what's going on, I take a little piece over here, and I look at what does that little piece over here look like. Am I expanding or contracting? So that's the Jacobian. That's the piece that we're after. Well, the way you find it is to say, I'm starting as a box, a rectangular box. When I map over, I look very close to what's called a parallelepiped. Think of it as a box that's been slanted. Now, we were able to say, oh, we can find area by taking a 2x2 determinant. But if you think back, we actually talked about one other thing you could do. You can take a volume of a parallelepiped by doing what? 3x3 determinant. So this is the volume of the parallelepiped that's estimating what's going on here. So it comes from a volume formula of local expansion contraction. Now if you just throw in the formulas and you just crunch through, this determinant becomes your rho squared sine phi. So it's not just random, it comes from a particular space. And that's it for today.